In this presentation, I will teach you decade or BCD ripple counter. This is the last type of asynchronous counter that we have to see in this course. After this, we will move to the synchronous counters. Before that, I will explain you few important points, and you will not find these points in your book, so they are important and they will help you to solve various questions if you are sitting for different exams. So let's see what is the first point. What it says, it actually gives you the relation between the triggering, the clock, and the up down counting. So if we have a negative edge triggered flip-flops, as in this case you can see all the flip-flops are negative edge triggered, and the output Q is given as the clock to the next flip-flop. So I can say the flip-flop is negative edge triggered, Q is used as the clock, then I have the up counter. And this case we have already discussed 100 times. All the time when we want the up counter, we use the negative edge triggered flip-flops and we take Q and give it to the clock of the preceding flip-flop that we have already seen. And if you remember, when I was teaching you the up down counters, I told you the best way to have a down counter is to have a negative edge triggered flip-flops and then take Q complement as clock. If you take Q complement as clock instead of Q, you will have a down counter. So these 2 points we have already discussed, but we have not discussed what will happen if I have a positive edge triggered flip-flop. So let's see. If I have a positive edge triggered flip-flop instead of negative, and I take Q complement as my clock, then I will have the up counting. And if I take Q as the clock with the positive edge triggered flip-flops, I will have the down counter. So this is a very important point that you have to remember. Every time in every book you will see they will use the negative edge triggered flip-flops. They will take Q or Q complement as the clock, and they will have a up or down counter. Most of the books don't talk about the positive edge triggered flip-flops, and definitely you can prove it by the timing diagram. You can prove it. I have already proved these 2 cases, and you can prove these 2 cases by yourself by using the time diagram. Now we will move to the second important point, in which we will talk about the cascading of the counters. What if I have 2 counters? The first counter is having the mod M, and the second counter is having the modulus N. What if I cascade them? What if I cascade these 2 flip-flops? What will be the resulting flip-flop? The resulting flip-flop will have the modulus equal to M N. So these 2 points are very easy and also very important. Now we can move to the decade or the BCD ripple counter. As it is a ripple counter, definitely the clock is not simultaneous to all the flip-flops, and we will see the circuit in few minutes. Before that, we have to discuss the number of states and the maximum count. So the number of states, is equal to 10, because we are talking about the BCD, binary coded decimal. It is from 0 to 9. So there are 10 states in total, starting from 0 0 0 0. The 4 bits are used to represent this state, and ending at 1 0 0 1. This is 9, this is 0. It will go all the way like this. And if I talk about the maximum count, then this is equal to states minus 1. So 10 minus 1, this will give me a 9. So 9 is my maximum count, and it will start counting like this. For the first negative edge triggering, we have 0 0 0 1, then we have 0 0 1 0, which is 2, 3, then 4, 5, 6, 7, 8, 9, and then back to 0. And you can clearly see that it is up counting, because for every passing clock pulse we have the higher values. So this is a simple thing to know. Now you already know we are using a 4-bit ripple counter, and in case of 4-bit ripple counter, the counting starts from 0 0 0 0 and it will end to 15, that is 1 1 1 1, but we want it to stop at 1 0 0 1. So what we can do, let me show you what we can do. First of all, let me write it down. This is QD, QC, QB and QA, the outputs of the 4 flip-flops, and here we will have our clock. This is initially, and then for the first clock pulse, second clock pulse, we are having 0 0 0 1 0 0 1 0 1 0 0 0. This is 8 and this is 9. Then 1 0 1 0 all the way to 15. So in decade counter, it should start counting from 0 and it will end count at 9 and then again go back to 0. So this is our decade counter. But we have to convert this 4-bit asynchronous up counter to the decade counter. For this we will see this particular case when the count is 10. So as soon as 10 has arrived, 1010, we have to reset our flip-flops. I hope you know the reset and set action in the flip-flops. For this we will use two asynchronous inputs, that is preset and clear. When clear is low, the output is equal to 0, and as you know 0 is reset, and in the same way is preset is equal to 0, the output Q is equal to 1, and this is set. But we want the reset action, not the set action. That's why I have connected preset to logic 1, because when preset is equal to 1, there is no effect of preset on the flip-flop. But we want to make clear equal to 0 as soon as we have 10 as the output, because we want to go back to 0 0 0 0 as soon as we have 10. So what we will do, we will use a NAND gate, we will use a NAND gate, and we will use a 4-input NAND gate. This is a 4-input NAND gate, and the first input will be QD, and as you can see QD is 1, so we will write QD here. Then we have QC, QC is 0, so I will use a NOT gate and then QC, and QB is also 1, so QB, and then finally QA is 0, so QA. Now let's see what is the output of this NAND gate when we have 10 as the output. QD is 1, QC is 0, but because of this NOT gate we will have 1, QB is 1, and QA is 0, so we'll have 1. So the output of this NAND gate is 0 when we have 10, and this 0 or the output of the NOT gate is connected to the clear of all the flip-flops, and this will reset the flip-flops and the output will equal to 0. So this is a simple thing that you have to do, but we can also reduce this logic little bit, because there is no need to take QC and QA in this logic. We can only have QD and QB. I will show you why. When QD is 1 and QB is 1, this is the only thing or the only possibility when we talk from 0 to 10. There is no output from 0 to 10 that will have QD equal to 1 and QB equal to 1. It is only 10. So as soon as QD is high and QB is high, it means we are having 10 and the flip-flops will have output equal to 0. So this is a simple topic that you have to remember, a BCD ripple counter, and there is a great chance of this question being asked in the exam. And I can say this is another case of counting up to a particular value that we saw in the last presentation. By using the NAND gate and having the proper input, we can reset these flip-flops whenever we want, and in this way we can count up to a particular value. And in decade counter we are counting from 0 to 9, so as soon as 10 comes we have to go back to 0. It means we have to reset our flip-flops. It's a very easy and important topic. If you have any problem, you can ask in the comment section.